Here we have the Andromeda Galaxy, and it shows two globular clusters that are located, associated with the Andromeda Galaxy next door. These are very compact groups, spherical compact groups of stars that are above and below the plane of the galaxy, located in the halo of the galaxy. They are population 2, older stars. It used to be thought that globular clusters represented the dead end of stellar evolution, that these were older stars. Globular clusters didn't have a lot of gas. They couldn't keep their gas and dust because they're so compact. They'd easily lose it to the interstellar medium. Plus, their orbital motions take them up and down through the plane of the galaxy, and every time they go up and down through the plane of the galaxy, that strips more material away from them. So there just wouldn't be enough gas and dust within globular clusters to keep stellar evolution going to produce protostars and new stars forming. But boy, we have learned a lot about globular clusters, and they are very interesting indeed, especially the populations of stars within the globular clusters. The Milky Way has about 150 globular clusters associated it, with some of the more massive galaxies have as many as 13,000 globular clusters. One globular cluster is M15. M15 is about 35,000 light years away in the direction of Pegasus. It's in a very dark part of the sky, so with binoculars you can actually see M15. Because here is a close-up of it. It's very compact. It contains about 100,000 stars, and it is about 120 light years in diameter, so it's quite large. And if you look right here, going further out a little bit, here we have PS1, the very first planetary nebula discovered in a globular cluster. So this one, again, is 35,000 light years away, and this shows you, PS1, this planetary nebula, shows you the stellar evolution, young stars, that's still taking place within globular clusters. Here's our second globular cluster, NGC 1846. This one is in the Large Magellanic Cloud. It's 160,000 light years away. And this globular cluster is an example of how complex the stellar populations can be within these clusters. After extensive research and observations, because it was quite a puzzle for quite a while, because there are two different populations of stars within this cluster, they have the same metallicity. Now, there are population 3 stars, theoretical, the very first stars that ever were, that don't exist anymore, that have not been detected yet, that produce the second population of stars, and these are the older stars that you find in the nuclear bulge of the Milky Way, or all galaxies, or in the halos, the older stars, population 2, but they have a little bit higher metal content than the population 3 because of the nuclear synthesis producing heavier and heavier elements that get incorporated into those clouds of gas and dust that eventually form protostars and the next generation of stars. And now, the populations we have now that exist within the disk of the galaxy where stellar evolution takes place, we have population 1. So population 1 have a higher metallicity than population 2 than population 3. Bear in mind that all stars are still 75% hydrogen, 24% helium, and 1% everything else on average, but still there is a measurable increase in metallicity. So in this cluster, we have two populations of stars that have the equivalent metallicity. They should have all be about the same age, but they're not. They differ in age by 300 million years. So it is thought now that this globular cluster, NGC 1846, is actually a result of a merger of two different globular clusters, one 300 million years younger than the other one. Also, in this particular globular cluster, right down there is that little teeny tiny little circle of green, which happens to be a planetary nebula. For a while, they weren't sure if this planetary nebula belonged to the cluster or happened to be in the line of sight. I think most thinking now agrees that it does belong to the cluster itself. Now, how do you determine the age of a globular cluster? How do you know there's two different populations of stars in there with two different ages like that? Well, let's go back to the HR diagram. The HR diagram, one of the things that you know about stars once you plot them on the HR diagram, that gives you an idea of their age. If you are located on the HR diagram where the sun is, you know you have a lifespan of 10 billion years. Once it reaches 10 billion years and runs out of hydrogen, then it starts to evolve. So you know that a white dwarf is more than 10 billion years old, because it took 10 billion years to even get to the point where it would become a planetary nebula and a white dwarf. When you plot stars on this diagram, you have an idea of their age. And you know that on the main sequence itself, where hydrogen to helium fusion is taking place, the stars at the very upper left-hand section of the main sequence, they're very, very massive, very, very hot. Hydrogen is fusing furiously, and some of those stars have a lifespan of 10 million years compared to 10 billion years for the sun. So if you then take all the stars, and either in a globular cluster or an open cluster, any cluster of stars, you can plot just the stars in that group of stars on an HR diagram and see where the turnoff point is on the main sequence. Now, a lot of these HR diagrams that involve globular clusters, instead of using spectral class, they will use the color index. So this one has B minus B. Remember, there is the UBV photometric system that classifies stars by temperature by looking at the differences in magnitude between two different filters. So if you look at stars with a B, blue minus B visual filter, you end up getting an index that is directly associated with the temperature of that star. So the hotter stars are negative. You see negative 0.25 on the left-hand side, and it goes over to 1 plus on the other end, horizontal end of this HR diagram. And right there, where you see the vast majority of stars turning off the main sequence, that's the age of the stars. Here are a few examples. For instance, up in the upper left-hand corner, we have a young cluster and an old cluster. And you will see on the young cluster that the turnoff point is quite high up the main sequence, because this one is very young, because only the most massive stars have evolved off the main sequence. So if you compare that with one beside it of the older cluster, you'll see the turnoff point is much further down in the main sequence. So it has taken more and more time to go as those stars evolve off the main sequence. They're going to do it from the top, where they have the shortest lifespans, down to the bottom where they have the longest lifespans. So the further down the main sequence that turnoff point is, the older the cluster is. So you will see lots of diagrams that show you the relative ages of different star groups. On the right-hand side, we have 1, 2, 3 that are 3 different clusters of stars. The one on the upper right, that's the Pleiades. It's fairly young still, but not the youngest, that's for sure. But if you look at the bottom, M67, that's also an open cluster of stars. You can see that most of its stars have now turned off the main sequence. The turnoff point is way down there, so that one's very old. In fact, the Pleiades is a few million years old, but that one is about 5 billion years old. And on the lower right, we have a globular cluster that has a turnoff point that ages it at between 12 and 13 billion years of age.